Is the mic is on? Okay, great. So I think we're going to get started this morning. So welcome to the third day of the Keystone Center's independent science panels on the Pebble Mines baseline studies. We had an interesting day of discussion yesterday, and I think we'll have at least that interesting or more interesting discussion today. Today we're going to be talking about hydrology and water quality, sort of a continuation of yesterday afternoon's discussion. We're going to lead off with talking about groundwater hydrology and those baseline studies, and then this afternoon we're going to talk about water quality. In a few moments, I'm going to turn the podium over to Kirk Nordstrom and Philip Verplank again from USGS to be our moderators. There is a slight change in the schedule this morning to accommodate a little bit of lengthier presentations by Pebble consultants that we hadn't anticipated yesterday. We want to make sure we have an opportunity to do that. So we are going to have the lengthen that discussion by about 10 minutes. So we're going to go from about as soon as we get started until about 9:40. And then we're going to have a break at 9:40 for 15 minutes, and then we'll come back. When we come back from that break, we'll go into the panel discussion and then the open discussion. So what we're really doing is moving the break up a little bit to accommodate that. I don't think there are any other logistical things that I need to tell you about. Oh, other than if you could all put your cell phones on silence or vibration or turn them off, that would be great. It came up a couple times yesterday, so we just wanted to anticipate that. The rest of the day will look very similar to the way we've been structuring this. The end of the day, we want to get preliminary input on panel members' recommendations, and I think what we'll probably make sure that these are that everybody understands that these are just preliminary, because the panel members will have gone through this day and heard this discussion and haven't really had time to really think about it. When we did this yesterday, they'd had a full evening to actually think about what recommendations might be, and so the recommendations are kind of an evolving thing for us, and I think we'll have more fleshed out recommendations in our report. But we want to get their feedback, get as much feedback as we can from sort of what they're thinking. So we'll have that, and then we also have on the agenda at the end of the day an opportunity for Pebble to comment on this set of discussions. So the geology, geochemistry, hydrology, and water quality discussions. So. And then we'll wrap up the day. And then I want to remind everybody that we have another panel next week on Tuesday, Wednesday, and Thursday. Same time, same place. Topics will be fish, wildlife, habitat, and socioeconomic, cultural, and subsistence issues. So I think we'll get a lot of interest in that. That should be interesting discussion. So I will go ahead and turn this over to Kirk and Philip, and they'll set up the panel discussions.
Well, good morning and welcome, and thanks, Todd. So this session is the second session in our hydrology and water quality panel. Yesterday we went through climate and meteorology, looking at sort of the amount of precipitation and how it reaches the site, and then went through a bit of the surface water hydrology, and today we're moving into groundwater hydrology. So we have the precipitation reaching streams, rivers, ponds, and now it's a discussion and understanding on how this water reaching the surface gets into the ground and how it moves through the site. There will be two presentations this morning by consultants associated with Pebble. The first presentation will be on the water balance. I think it's on the water balance. Well, the first part is by Rod Smith with Schlumberger Water Services, He's a geological engineer with over 30 years of experience. He has contributed to groundwater studies at mine sites in the United States as well as other countries in North and South America. These studies include mine dewatering, open pit slope stability, embankment stability, mine rock dump stability, water quality characterization, seepage control design, water quality remediation, surface water and groundwater interaction, and water supply. He has provided direction to the Pebble Groundwater Hydrologic Program since 2004.
And his co-speaker is Hugh McCready, who's a groundwater hydrologist and hydrogeochemist. He has a master's degree from the University of Waterloo and 22 years of experience in assessing groundwater conditions at existing and proposed mine sites. His expertise is in both field investigation techniques and the practical application of 3D groundwater flow and transport models in order to simulate regional groundwater flow, contaminant fate and transport, groundwater supply systems, dewatering systems, and environmental impact. He's given courses on groundwater modeling in 8 countries around the world and has conducted groundwater assessments at existing and prospective mines in Canada, the U.S., Peru, and Indonesia. He joined the Pebble team in 2004 and developed protocols and trained the field staff in field techniques for logging drill holes, installing instrumentation, monitoring water levels, conducting hydraulic tests, and collecting groundwater samples. Since then, he's been the lead hydrogeochemist for assessing groundwater quality and has developed a groundwater model representing the baseline conditions at Pebble. Okay, Rod.
Thank you very much. So just to clarify, my discussion is about the groundwater hydrology setting of the Pebble site, and will include an overview also of the water balance methodology that we used in order to relate the groundwater regime to the surface water regime at the site. One of the most important aspects of a groundwater setting is the geology. And I know that there was a discussion on geology 2 days ago, and so you do have a little bit of an understanding of the site. To the west, the circle is the apparent location of the deposit, approximately, and to the west of that is Kaskanak batholith, a large intrusive. And some of that intrusive material has injected into the site. Okay, I'm going to have to be careful with the buttons. As dikes and sills as part of the mineralization. To the east of the site is primarily tertiary rock, which is later than the is a later deposit than the mineralization. So does not have any of the ore in it. So this is a close-up then of the mineralized area, and you can see in here the pink areas which are intrusive amongst a lot of the sedimentary. The important part of this is that there are a number of faults that have been identified that go through the mineralized area. This is not unusual for a porphyry copper deposit. On the far right, to the east of the deposit, are the ZG faults. And these are quite a bit of displacement on these faults, forming a graben, that is a downdrop structure to the east. We were very fortunate to have Tom Hamilton map the superficial geology for the site. He's a USGS Emeritus glacial geologist, and he was able to identify the source of much of the superficial material at the site. And what's illustrated on here, just to okay, see if I can. This is Frying Pan Lake in here, and the deposit area is in about the center of the screen. These illustrate the tongues of glaciers that advanced into this site 10,000 to 25,000 years ago. Over much of Canada, northern Canada, the ice was thousands of feet thick at this time. But at this site, we have the glacial terminuses. So we're right at the edge of that big continental glaciation. As a result, we have some very specific deposits, and shown here are the terminal moraines and recessional moraines that were formed at that time. So this is Tom's map, and we can see here a lot of blue material in here, blue map. Now those are deposits from glacial lakes, and the deposit area is just again north of Frying Pan Lake. Really is north of Frying Pan Lake. So you can see that there's the lacustrine materials, glacial lacustrine materials, result in relatively low permeability material in the vicinity of the deposit. However, in all three of the catchments, the North Fork catchment, the South Fork catchment, and the Upper Tulare Creek catchment, there are significantly large deposit of glacial outwash deposits. And these are very permeable sand and gravel deposits in this area and in the South Fork and to the east of the Upper Tulare Creek. Another aspect of the glacial activity is that it was mainly depositional. There was very little erosional activity. So during that period, the frost activity in the rock resulted in displacement or slight movement, opening of the top of rock. And so over most, if not all of the site area, we have a 10 to 50 foot thick area of relatively high permeability rock. So just to summarize then, the faults are present in the deposit area, and they do provide groundwater pathways and blockages, and that can result in compartmentalization of the deep groundwater system. The freeze-thaw activity, particularly through glacial periods, resulted in a thin 10 to 50 foot disturbed zone at the top of rock. The glacial outwash sand and gravel and ice contact deposits have left extensive permeable deposits in all three of the catchments. And there is one large glacial moraine, which is composed of permeable sands and gravels. And the glacial lakes have left extensive low permeability materials in all three drainage areas. And terminal, recessional, and lateral moraines are mostly composed of low permeability silt, sand, and gravel. There's been a lot of hydrogeologic testing done. These include 9 pumping tests in each of the 3 basins. They were pumped with the airlift method and monitored in adjacent piezometers. There's been a number of slug or single slug or response single well tests. So that involves a short-term test at a well to get an idea of the permeability. There's been packer tests during drilling in bedrock, as much as over 400 of those. And there was a multiple depth cross-hole test to a depth of 4,000 feet in the center of the deposit area. This is just a picture then of a well development that's required in order to clean out the silts and fine materials from the screened interval prior to doing a response test to get a more realistic idea of the hydraulic conductivity of the formation in the area of the installation. This is a plot just illustrating the distribution of hydraulic conductivity from the response test and pumping test outside of the deposit area. So the median, that's the 50 percentile, so in about the middle of the plot, is 10 to the minus 4 meters per second. Now, typically when we install a piezometer or a monitoring well, we try to install it in a more permeable horizon in the hole, not the impermeable horizons. So this is representative of the more permeable material on the site. So as I said, the median here is about 10 to the minus 4, which is quite a permeable material. In the deposit area, a similar plot, both both in bedrock and in the overburden materials, results in a median of about 2 times 10 to the minus 5. And again, that's a result of really being in a lot more glacial lake material, and where we have sands, finer grained sands, than we get in outwash materials and within alluvial deposits. This is a plot of packer tests that were carried out in the deposit area, and illustrating that, as I was saying a minute ago, in the deposit area, the near surface hydraulic conductivity materials in the slug test, we were getting 2 times 10 to the minus 5 meters per second, which is right out near the right-hand side of this plot near the surface. And then as you go down with depth, the hydraulic conductivity gets lower. That's to be expected with depth. If you have several hundred feet of material overlying a fracture, and in bedrock, most of the water is flowing along fractures, it pushes the fracture shut, and it's more difficult for the water to pass through it. So all other things being equal, you expect the hydraulic conductivity to become lower with depth, and that's what the tests have illustrated. There are some tests in here that were carried out later to on specific identified faults that have higher permeabilities. And again, one might expect that there is a difference in stress distribution and a difference in fracture density near the faults. This is this deep testing that we did to 4,000 feet. We had one hole installed with about 50 locations where we could measure pressure, and that's illustrated on the right-hand side. You can see a large number of little bars, and that's the measurements, the large number of little bars illustrating the measurements where we were able to take measurements as we drilled and pump tested this adjacent hole. So in this adjacent hole, these blue bars are areas that we drilled and then airlift tested to see what kind of response we would get in the adjacent drill hole where we were measuring the pressures. So we would drill down, do the pump test, and then cement off or pack off the upper part of the hole, and then drill the next set of hole and then pump that, and so on, all the way down to 4,000 feet. Based on all those testing intervals, we identified what we classified as hydrogeologic units, so HG in between the black bars, and then assigned hydraulic conductivities to those based on the test results that we get. So above about 1,500 feet, we're in tertiary materials, and the hydraulic conductivity, as you can see, is dropping quite a bit with depth. Some due to the increased stress levels, but also at the bottom of the tertiary, it was a very competent conglomerate. And we were able to calculate a hydraulic conductivity that high only because we had actually opened up the fractures by installing a packer and pressurizing it until we actually got some take in the water. So it was a very low permeability environment. Once we went below about 1,500 feet, then we were into the pre-tertiary, mostly granitic type rocks. And again, the permeability came up a bit and then again dropped with depth. One of the interesting things after when we installed the first hole, it was in place for a couple of years prior to doing the pump test in the adjacent hole, was that in these lower parts, although the permeabilities are similar to moderate depth in the tertiary, the pressures that were created in those zones as a result of drilling and installing the packers and inflating them took 2 years to dissipate. So although those hydraulic conductivities around the hole seem moderate, not low, the indication is that those installations are compartmentalized by the faults in the area, such that it takes a long time. It took a long time for those drilling and installation effects to dissipate. And in addition, when we looked at the water quality in those deep holes, and Hugh may discuss this a bit more later, the TDS was significantly higher than in the fresher, shallower environment. So the upper 600 feet of bedrock was responsive to seasonal recharge events and changes in barometric pressure. The response to the surface effects like that declined rapidly below 600 feet, but then we could see the response to earth tides at those depths. The hydraulic conductivity decreases with depth down to the base of the tertiary, and the basal conglomerate of the tertiary had a very low permeability. The base of the tertiary was defined by the ZE fault, where there's a sudden change in piezometric levels. Below the ZE fault, the hydraulic conductivity increases and then again decreases with depth. A slow recovery of drilling and installation-induced pressures is indicative of a system compartmentalized by faulting systems. There was a large number of springs and seeps that were inventoried on the site, and a small subset of those, about 25 I believe, that were selected for monitoring and sampling. That is an important, those springs, some of them quite high on the slopes, are an important indication of the groundwater regime on the site. Drill circulation monitoring. There's a lot of drilling on the site that is not specifically designed for hydrogeology, and particularly those for resource drilling. A lot of information is available, but it's not designed for groundwater monitoring. But for many of those holes, we were able to have PLP monitor the drill circulation. So in some cases during drilling, there may be some artesian flow in some depths, or there may be a loss of some of the drilling fluid, indicating that perhaps that's a higher zone of hydraulic conductivity. So these notes provide a qualitative indication of the presence of permeable horizons for consideration in the ongoing investigations. Jamie talked quite a bit about the low flow stream gauging. We have a remarkable set of data on this site. As he said, 26 continuous gauging station, and I can't remember the number, another additional something like 25 stations that specifically designed to improve our understanding of the low flow conditions along the streams. The stream flows during dry season supplied almost entirely by groundwater discharge, and therefore are a primary source of data for documentation of the groundwater flow system. The other thing that was done was to map the stream reaches with winter open water. The normal condition in a stream is that their groundwater discharges to the stream to create the low flows, but in some cases there's stream losses, and in other locations there's exceptionally high discharge areas. These open water areas are documentation of the exceptionally high discharge areas. So this is just an example, and I think Jamie showed this also yesterday of the open flow. And they documented no flow conditions in this long section of the South Fork, and then this open water zone in this upwelling zone in the South Fork. And then we have a groundwater discharge into this upper Telerik tributary to the east. That, combined with the actual measurement of low flows, has really been a huge benefit to the groundwater program. There was a question yesterday about discharge along the low flow conditions along this that was mapped as dry, and whether we really knew whether it was dry through this whole section. We know that it does get dry in this area in several areas, even in the summertime. In some summers we've had low flow conditions. And the piezometric levels in the summer are nowhere near as low in this area as they are in the winter, and it's a gravel area. So I just have here a plot of piezometers in this area and here, and in this area and here. Upstream of that, up to Frying Pan Lake, the stream is all year round is well above any of the piezometric levels, so it's always a losing reach. Groundwater levels groundwater levels are measured in a number of holes on the site. We've measured monthly at over 400 locations over some period of time. They're measured in geotechnical holes, in holes specifically designed for groundwater monitoring. They've been measured in drive pipe installations to understand the local conditions around some wetland ponds. There have been vibrating wires grouted in place in some locations to get some data at greater depth where it's not as easy to install standpipes. The West Bay multiport installation I was illustrating to you a little earlier, we're measuring piezometric levels at 50 locations with depth at those on a monthly basis. And of course, their groundwater levels are implied from seeps, springs, and surface water bodies, and those also are all very important bits of information. So in the South Fork, Cockatoolie, the upper part of the South Fork, although there is a lot of glacial lake fine-grained materials that does not transport groundwater well, we do have a number of gravelly or sandy materials which we have identified from the drill hole mapping combined with the superficial materials, and those are illustrated in color here. They are sometimes gradational. An example is this large deposit in here. It's very coarse-grained and thicker in the northwest corner and thins towards the outside and towards the south. This is a smaller body, but is a sand and gravel body. This is a thin body that sits in a bedrock low. This is a tremendous amount of effort has gone into drawing cross sections and designing the drill program in order to define these units. To the south of Frying Pan Lake, the permeabilities are much higher. And the aquifer bodies are much larger and more continuous. Jamie was discussing the cross-boundary flow from the South Fork to the Upper Tulare yesterday. So this is Frying Pan Lake and the South Fork, and this is the Upper Tulare Creek off to the right. And this is an interpretation of the groundwater table in that area. And we have a divide then where the water levels are highest, indicating that water is moving towards the South Fork, to the west of the divide, and towards the Upper Tulare to the east. And this is very close to the surface water divide. That's the water table. However, if we plot piezometric levels at greater depth in a lower aquifer, we see that the divide has moved over quite a bit and actually takes in some of the aquifer underneath the South Fork, so that we have groundwater now moving out from the South Fork to this Upper Tulare Creek tributary, this UT 1190 Springs, as well as groundwater, but of course some of the groundwater is still moving to the south and west to the upwelling area in the South Fork Cockatoolie River. You keep track of my minutes? So similarly, we've done hydrogeologic characterization of the North Fork. Aquifers in the North Fork Cockatoolie River Valley include outwash and alluvial sand and gravels, which are present downstream of the Kvichak stayed terminal moraines. And there's less extensive outwash delta and fan delta deposits downstream of the Iliamna stayed terminal moraine within Big Wiggly Lake Basin. And there are thin sand and gravel alluvial aquifers within tributary valleys. Glacial lake deposits influence the distribution of permeable material through the Big Wiggly Lakes Basin, and that's the upper area of the North Fork Cockatoolie River. There is a potential for some cross-boundary groundwater flows from the North Fork Cockatoolie River Valley, some minimal from the North Fork Cockatoolie River headwaters to the Upper Tulare Creek at the saddle. And based on available drill hole data and groundwater levels, any such cross-divide flow is expected to be relatively small. And there's also potential from the North Fork Cockatoolie River headwaters into the Chilitna River drainage, again at the saddle. This is also expected to be a limited rate. However, we don't have any drill holes at that saddle, and it's quite a long ways from the active, from the deposit area. In the Upper Telerik, aquifers in the Upper Telerik Creek Valley include extensive ice contact meltwater deposit, outwash deposits, and deltaic deposits of the Iliamna stayed east of Upper Telerik Creek. And I showed that earlier on when we were looking at Tom Hamilton's map, a large plain to the east of Upper Telerik Creek, which is covered by internally drained depressions. So in that area, there's almost no runoff. It's all of the groundwater hitting the ground, enters the groundwater system, and moves towards the Upper Telerik Creek as groundwater. And Jamie was pointing out that the Upper Telerik Creek has a very high base flow, and that's the primary reason for that high base flow in the Upper Telerik Creek. So groundwater calculations, we've taken we use two different types of calculations in order to fully understand the groundwater system on this site. And the first is a site-wide water balance. And Jamie likes to call this a watershed model to remove it from other types of water balances that are done for mining projects. But it was completed to constrain the groundwater recharge and discharge rates, which reduces the non-uniqueness of a groundwater model. This procedure was also very helpful to define surface water and groundwater interaction on the site. And then what we use that in combination with the groundwater model in order to fully understand the system. And the groundwater model, of course, includes the physics of groundwater flow, which is not within a simple water balance method. So the water balance primary inputs were monthly Iliamna airport precipitation and temperature records, which are available from 1942 to present, and monthly Pebble site precipitation and temperature records, which are available since 2004, and site stream flow records, which are available since 2004. So the stream flows were simulated with the water balance method from Iliamna climate records, which were adjusted for seasonal and site variables. That was discussed a little bit again by Jamie yesterday, and also in the meteorological talk. We needed to make adjustments because of the inability to collect all of the precipitation data in this high wind environment. There's also the potential for variations around the site as a result of rain shadow effects and snow blow conditions that will influence the expected distribution of precipitation around the site. So the calibration focused on developing an appropriate range of flow values annually and seasonally, and the calculation allowed simulation of stream flow records back to 1942. That is, we calibrated the data to the flow records we had available from 2004 to, at the time of the EBD, was 2007. And then using those same parameters, we were then able to look and say, based on that calibration, what kind of variation do we get in flows from the full record from 1942 to present. So it gives a better understanding of what the expectation might be of low flows, dry flows, and wet flows over that period. So the water balance was calibrated by adjusting calibration parameters to visually match the calibration targets. And the calibration targets were basically the surface water flows, while remaining within a physically reasonable range. The total flow was calibrated by adjusting the net precipitation, that's the total precipitation minus the sublimation and the evaporation, to visually match the measured stream flows on a mass plot. And the base flow was calibrated by adjusting recharge to match the volume of the base flow, and the discharge factor to adjust the slope of the recession or drain down curve. And then we had a third mid-range flows, which might be representative of short-term surface depression and interflow values. they were adjusted also with a surface water detention and release element similar to groundwater, but of course responding much faster. So the site-wide water balance subcatchments, where we had long-term data early on in 2005, 2006, we set up these basic 15 catchment areas, and we subdivided those catchment areas by elevation bands. So the different colors on here are the different elevation bands. The elevation bands have 500-foot intervals. And the lines outline the different catchment area numbers. This is what I was saying, that we look at the mass plot to look at the total flow, and we're looking at saying this is the cumulative amount of flow that is measured. The brown points are the cumulative amount of flow that is measured over time. And then the blue line then is the simulated amount. So if we didn't get about the right volume over the calibration period, then we would have to adjust the precipitation in order to get the correct amount. And so that was one of the primary methods that we used. And then, of course, we didn't want to just have the total flows right. We wanted to have the flows in the winter about right, and the flows in the spring and the fall about correct. So in order to get the flows correct in the fall, we would have groundwater discharge, groundwater recharge to get this volume of water available, and then the drain down, the speed with which the groundwater discharge decreases over the winter, we would adjust that with the discharge factor. So because we're using Iliamna precipitation records, and that's not exactly what's going to happen at the site, and in fact I'm sure any storm on the site is actually a little different from one time to another. We're not really expecting to get each month exactly right. That would be sure, if you got that you would think there was someone had really cheated. But we do want to see that we get the distribution of flows reasonably represented. So this is the methodology that we used for that. We used essentially a flow distribution. So in this case here, for example, at 30 months, we have approximately 12 or 13 CFS. So there's 30 months on this site that have flows less than 12 or 13 CFS. We're looking at about 60 months of a record. So those 30 months represent mostly winter flows. So that whole left-hand half, 30 and less, mostly are mostly groundwater flows discharging on the site with very little contribution from surface water. So that really helps us then when rather than looking at individual months on the hydrograph record, we're looking at this distribution and making sure we're infilling it as best we can. And this is a pretty good match then. And then this is, so the one I was showing you was for a North Fork 119A. So that's a tributary, fairly steep tributary. And SK100F, that's a gauge which the deposit area is included in. And you can see that that it is a flatter line. So it has generally speaking, a bigger groundwater component and is less flashy than NK119A. And then, so one of the things that we got out of this at the end was we needed to have a precipitation distribution in order to make those work. And so we had an orographic effect, and we had local factors which varied. We had one precipitation model which had orographic effects, and then for each of the gauging sites we had a local factor which might look after rain shadow, snow blow effects. And that varied from location to location about plus or minus 10%, which in reality might be the error bars that you might also put on the flow measurements. So we really feel that we're as close as we can get. There's always room for improvement, but it's very close. So this is a precipitation distribution we end up with on that, and you can see that the high areas along these boundaries tend to be the high areas. We have a much higher precipitation, over 70 inches per year. And then in these lower areas, we're down closer to, more like 40 inches per year. Now, that's total precipitation. The net precipitation, typically we're looking at about 14 inches per year of sublimation and evapotranspiration. And then also this, we have a distribution then of groundwater recharge as well. So these numbers then that are in here for groundwater recharge over these large broad areas, they go to the groundwater modeler, Hugh, and he'll be talking here in a bit. And he redistributes these groundwater recharge areas based on slope and superficial material types. So just this is then just some simple schematics to illustrate how we think about the system in this area. This goes across all of the three valleys, the North Fork on the far left and the Upper Telerik on the far right, where our expectation is that we have quite high recharge rates into the broken rocks and the typical northern environment with a lot of stones on the surface. Thank you. And so we expect quite a lot of recharge, groundwater flow towards the valley bottoms and discharge into the valleys, and that's true for these two smaller valleys as well. Near the deposit area, we have moraines on the valley walls with limited recharge, but again, on the ridges we see some recharge, and again, discharge into these thinner aquifers in the valley bottom. And then in the Upper Telerik, the stream is near the side of the overburden deposits, but we have a large high recharge plain to the east of the Upper Telerik, providing a lot of groundwater flowing towards the stream. Looking downstream on the South Fork Cockatoolie River, then in the deposit area, again, we have a lot of fine-grained materials, mostly groundwater discharge to the stream in this area. And then we flow in, the river flows out over top of a very large aquifer with high losses, stream flow losses to the aquifer. And then as that aquifer thins and narrows, we get large groundwater discharge back to the stream, restoring the flows. And in the North Fork, we have a similar environment, although the aquifer is smaller. In the Big Wiggly Basin area, we have quite a lot of lake deposits, glacial lake deposits, with rather limited amount of groundwater discharge, but always a groundwater discharge to the stream. And then coming out over top of the aquifer, the stream bed is elevated above the groundwater table, so we have high losses. And again, as that aquifer thins, there's significant gain to the stream. And in the Upper Telerik, we don't have quite that same environment. We do have an outwash deposit near the very upper end, and it results in the gauge in that area having a large groundwater component, but the flows are generally low there. And then we have a large section of the stream that's over glacial lake deposits, relatively low discharge rate, but all discharging in that area. And then in this section, the lower section, on this section, most of the water is contributed, most of the groundwater is contributed from the large aquifer to the east of the Upper Telerik, with of course some groundwater coming in as a result of that cross-boundary flow from the South Fork into the tributary UT 1190. So summary, glaciers have deposited large superficial aquifers in an area that result in substantial groundwater surface water interaction. This setting has also resulted in interbasin transfer of groundwater. In the deposit area, glacial lakes dominated so that silty units with some sandy layers are present. Regional terminal moraines are within the study area. The glaciation was depositional rather than erosional. Frost-damaged rock was therefore left in place and results in the presence of an upper bedrock groundwater zone across the site. Hydraulic conductivity generally decreases with depth in the bedrock, primarily as a result of confining stress. Fractured zones adjacent to faults often have increased hydraulic conductivity, and the presence of fault gouge causes a decreased hydraulic conductivity along the faults. Intersecting faults within the area are expected to compartmentalize groundwater zones in bedrock. This phenomenon is consistent with the conditions measured in the West Bay multi-level monitoring well. And the compartmentalized groundwater regime and the presence of higher permeability near surface materials results in negligibles, maybe not a very good word, but a regional groundwater system which is very much dominated by the local groundwater flow system. And that lower permeability is expected to inhibit the inflow of deep groundwater into the proposed mine.
Thank you.
Did I make it?
Yeah.
Change the name card. So I'll make sure I understand which button to press here. Okay, I'm good. Good morning. So once we finished our conceptualization of the site that Rod drove primarily, we continued to work together to build the groundwater model, which is a representation of the physics of the groundwater flow underneath the ground. And what I'm going to do is just show you just a few slides just to give you a little bit of insight into the kind of work that we did with the groundwater model, kind of how we built it, and the kinds of results that we got in terms of simulating the baseline conditions at the Pebble site. So Rod alluded to this a little bit in his talk, that what we've done is to take an integrated modeling approach consisting of two components. The first component is the hydrologic water balance that Rod has been working on, and that takes into account all the hydrologic flow components such as precipitation, evapotranspiration, recharge, all those kinds of things. And we're having that be consistent with the groundwater model that we developed. So I put together a little set of cartoons here to just give you a feel for what we mean by that. It's a lot of words, and sometimes it helps to have a cartoon to illustrate what we're talking about. So with the water balance, then what we're talking about is this box here, and the water balance is purposely accounting for both all the surface water flows and all the groundwater flows at the same time. So this includes precipitation, which is going to be net of evapotranspiration, sublimation, and storage in the surface water system. It'll also account for recharge into the groundwater system. And then it also accounts for flows through the groundwater system from one watershed to the other. You might remember the slide that Rod put up showing all the separate catchments that we've divided the study area into. There's about 14 altogether. And then, of course, as Rod has mentioned, there are lots of places where groundwater is discharging into the streams. And so the water balance takes that into account. It adds in the runoff that's flowing across the surface, and these two flows then combine to produce the measured stream flow in all the creeks on the site. Now, the groundwater model is a little bit different because what it does is it takes this part of the water balance, and instead of just doing a balance on the water, it actually simulates the flow. So we actually have layers within the groundwater model that represent the sands and gravels, the silts, the fractured bedrock, the more competent bedrock, all those things that Rod talked about. We actually represent those physically in the groundwater model, whereas in the water balance model, they're represented just as kind of buckets of water. And the reason we're doing this is we want to verify that the kinds of numbers that we're using in the water balance are actually reasonable when we start to consider all the physics of groundwater flow. Now, most of these surface water components are not included in the groundwater model. So, for example, we don't simulate surface water storage, sublimation, evapotranspiration, those kinds of things explicitly in the groundwater model because they're already taken care of in the water balance. But in the latest revision of the groundwater model, we actually are starting to consider stream flow as well. So explicitly modeling the stream flow within the groundwater model. So then the correspondence between these two models is something like this. They both have groundwater recharge, they both have groundwater discharge, and they both have groundwater flows between the watersheds that we're looking at. Now, one difference here with this correspondence is that whereas this is represented with a single number, of course in the groundwater model we're actually accounting for the different flow rates in the different hydrogeologic layers within the flow system. Then the other thing that distinguishes the groundwater model is that we have several hundred piezometer installations that Rod talked about, and we actually consider those explicitly in our simulations of the groundwater flow system. So we'll have some monitoring points installed in deeper aquifers, some monitoring points installed in shallower aquifers, and we work with those different water levels to develop a reasonable representation of the system. So back to Rod's watersheds. We've developed numbers for these watersheds. This is the South Fork Cocktooley watersheds that we're looking at here, or subwatersheds or subcatchments. We use those words interchangeably. These are the Upper Tilleric subwatersheds. These are the North Fork Cocktooley subwatersheds. And what we've done is to avoid artificially constraining the groundwater model, we've extended the boundary outward somewhat to include some other subwatersheds like this. And I put together this little summary table just to summarize all that stuff. So in terms of the components of the water balance considers all of them, so all of the surface water processes, whereas the groundwater model is considering the groundwater components of the water balance. Both of the models are divided into the same subcatchments so that we can compare the flows between the two models for each of the subcatchments. In terms of distributing the flow within each subcatchment, the water balance does not do that. So for a given subcatchment, that's a lumped flow, as we call it. Whereas in the groundwater model, we distribute flow within that catchment. And I'll give you an example of that in a couple of slides. And then finally, explicitly considering geology, groundwater elevations, and groundwater flow paths. The water balance does not do that, but the groundwater model does. So you can see how each of the models complements one another, and the aspects that one model does not cover, the other model does. And then we have the linkages between the two to ensure consistency. So in terms of ensuring consistency, then what we're talking about is monthly recharge, monthly net groundwater discharge, monthly interwatershed groundwater flow. So this is what I mean as an example of flow distributed within a watershed. So this is one of the subwatersheds on the South Fork Cocktooley. In fact, it's the one where we have the drying reach, and the recharge in the water balance is just considered as a lumped number for the whole subcatchment. Now these colors here represent different recharge rates at different locations within that subcatchment. And so the blues are relatively low numbers and the reds are relatively high numbers. And this is for a particular month. Because of course from month to month the recharge changes. So so you can see that one of the differences is that we consider that different geologic materials have different recharge rates within each subcatchment. And then what we do is we apply those recharge rates from month to month. And you can see that the recharge rate goes up and down according to when the spring snow melt is occurring and according to when we have fall rains. This particular plot is for the total recharge for the whole model. I just wanted to give you a feel for how we model the system over time. So then, as Rod and Jamie have been discussing frequently, there is a lot of groundwater, surface water interaction at this site. And I was really happy the first field trip that we made up here in 2004, and we were out going along the South Fork Cockatoolie River. You can actually see the groundwater discharge, and this is very rare for a hydrogeologist and exciting for me. So you know I'm a very nerdy guy. I get excited by seeing this. So this is a picture taken from what we call the groundwater upwelling area and the South Fork Cockatoolie, and these little rings that I hope you can see from where you're sitting. I can't quite see them on the angle here. Represent the groundwater that's discharging up into the stream. And then, as Rod has talked about, we also have the other end of the spectrum where in certain times of the year, specifically during the winter flow period, and from time to time in the summer, including 2004, there is this stretch of the South Fork Cockatoolie that goes dry. And so I've put together a cartoon to illustrate an example of the seasonal effects of groundwater surface water interaction then that we are simulating with our groundwater model. So the way it might go at some locations within the study area is that in the wintertime, when the stream is dry because there's no runoff and because the water table is below the bottom of the stream, there would be no leakage from the stream into the groundwater, and similarly there would be no discharge from the groundwater system into the stream. Then spring runoff comes along, the water table comes up, and we have surface water flow coming into the stream, and so then we might actually have groundwater discharge into the stream at some locations. Now, I'm not talking about, this is not a site-wide phenomenon I'm illustrating here. This is an example of seasonal effects that we might see at certain locations. Then in the summer, there might be enough rain that we have surface runoff coming into the stream, which would keep water in the channel, but maybe not enough recharge to keep the water table high. So then perhaps the flow direction then reverses again. Perhaps we have leakage going into the stream, leakage going into the groundwater system. And then finally, in the fall, perhaps we might have the water table coming up again, and again we return to a discharge condition. And then finally, winter, back to no leakage. So one of the things that we did was, while we were working on adjusting the parameters for the groundwater model, we wanted to have the flow rates calculated by the groundwater model be consistent with the water balance. And so what we're looking at here, or what I'm about to show you, is the groundwater discharge compared with the water balance. And so what I'm showing in this particular example is the total groundwater discharge by watershed. So these are the watershed numbers that I illustrated on a previous slide, and then each of these dots represents either the groundwater model or the water balance model. So the blue then is the groundwater model, and the pink is the water balance model. And the whiskers that you see on the pink dots represent the uncertainty in the water balance calculations. And so if we have the groundwater calculations falling reasonably within these whiskers for each watershed, then we feel that the two models are internally consistent and telling the same story. Now, we also have field calibration targets, specifically groundwater elevations, which were measured monthly from 2005 to 2008. We have average monthly stream flow that's measured in the field. And with the latest revision of the groundwater model, we're able to compare our simulated stream flows with the measured stream flows. We have late winter groundwater discharge on an annual basis for all of these years. And the reason that we're interested in doing both groundwater elevations and flows, or looking at those numbers, is that calibrating to both heads and flows really increases the model uniqueness, because many models are calibrated to only groundwater elevations, and it can look very good, but it's non-unique when you do that. You could have many combinations of parameters that calibrate equally well to groundwater elevations but calculate completely incorrect groundwater flow rates. So by having a comparison of the groundwater model output with average monthly stream flow and late winter groundwater discharge, then we're really able to constrain the model much better. So first of all, looking at groundwater elevations, all of these red dots on this picture illustrate all the monitoring locations that were considered in our model calibration, 293 piezometers in all. And I don't have time to go into all the details today, so I'll just show you the big picture. This is a plot of the modeled versus observed value for all of the monthly measurements, and so that means that the modeled values are plotted on this axis and the observed value is plotted on this axis. This is a basin and range environment, so you can see that the range of values is quite large. And what we're seeing is that the dots for all of the monitoring locations line up in a reasonable way on that line that represents a match between the modeled and observed values. So we have some statistics here that I don't really have time to explain exactly what they are, but basically when these statistics, the residual mean, the absolute residual mean, and the scaled RMS are small numbers, then that means that we're doing a reasonable job of matching the field conditions with the groundwater model. And so on a model-wide basis, then these numbers are actually looking quite good. I'll just briefly show you another example of the kinds of things that we look at when we're evaluating how well the groundwater model is simulating the actual system. These are plots of the change in groundwater elevation versus time. So then each of these blue dots represents a field measurement at a given piezometer. And then the red line represents the simulation results from the groundwater model. So you can see that the blue dots go up and down on a seasonal basis in response to the spring snowmelt and the fall rains. And similarly, the response of the groundwater model also goes up and down in response to the monthly recharge that we feed into the model. And these are 3 different locations. And it's a regional model, so I don't expect every single dot to be matched by what we're doing at this time. But what we can see is that overall, the kind of response that we're getting out of the groundwater model is looking quite good. Then the next thing that I talked about was calibration to stream flow. So this is average monthly stream flow that's plotted on this axis, and then these are the months plotted across here. The field data are plotted in these this light color here. The water balance is plotted in the infilled blue, and then the groundwater model results are plotted in red. And we're not so interested in the high flows because our purpose is not to try and predict peak flows. We're not trying to predict flooding or anything like that. What we're really most interested in is this part of the hydrograph here, that the way that the flows decrease in the stream represented by the model is similar to the way that the flows decrease as they're measured in the field. And so this is a location on the South Fork Cocktooley, somewhat downstream of the upwelling area. And we can see that the agreement between the field, the water balance, and the groundwater model is quite good. The next set of calibration targets based on field measurements we looked at was the late winter groundwater discharge. So it's really quite impressive. This is a flow gauging station on the North Fork Cockatoolie called NK100 LF4. This is one of the extra sites that Rod was talking about that is used specifically for measuring low flows in the wintertime. And I thought I would just put this up here to reassure you. This is the freezing line here, and this is the daily temperature. And you can see that, yep, sure enough, the temperatures are below freezing. So even in the dead of winter, we have some sections of the rivers that are indeed open water, as Rod was showing on his map a little bit earlier. And so what this looks like then along the South Fork Cockatoolie, so this is a cutaway, this is Frying Pan Lake, and this is the river channel here, and then I'm illustrating gaining and losing reaches along the South Fork Cockatoolie here, where this is what we call a losing reach, where it's leaking into the groundwater system. This is the well-known groundwater upwelling area where it's gaining, then losing again, and then gaining again. So it's a relatively complex pattern of gaining and losing reaches along this part of the site. And so what we'll do then is extract the flows that are calculated by the groundwater model and compare them with what we actually observed. So then the dots represent the field measurements, and the whiskers on those dots represent the uncertainty in those measurements. And then the various lines represent the corresponding flow rates that were calculated by the groundwater model. So this is the downstream. Yes, this is the downstream part here. This is SK100A, and you can see that it's representing the gaining and losing reaches along the South Fork Cockatoolie in a reasonable fashion. So in summary then, the model structure is set up in such a way that we have multiple hydrogeologic layers representing the geology at the site. We feed monthly recharge into the groundwater model to represent the changes in the amount of water going into the ground on a seasonal basis. We have the watersheds within the groundwater model set up to be consistent with the water balance so that we can compare the flows between the two models. And we're simulating surface water groundwater interaction. So we're demonstrating then that the models are consistent with recharge, groundwater discharge, and groundwater interflow between watersheds. Although I didn't show it today, when we are evaluating the model calibration, we do look at each watershed, because when you look at the big picture, you often miss some details that you need to attend to if you drill down to a smaller level. And then the other important part of checking the calibration is ensuring that the transient response of the model is appropriate at most monitoring locations. And then finally, when it comes to flows, we have calibration to groundwater discharge as well for multiple years and for all three of the primary drainages. So that's just a very brief kind of scratch the surface insight into the groundwater model to give you a feel for what it was that we did there and how it relates to the conceptual hydrogeology and the water balance. Thank you very much.
Thank you, Hugh. You may have considered that that's just scratching the surface, but I think a lot of us think that's quite a bit of information. And so now we'd like to have a break, take a break, and come back at 10 o'clock. We'll have our panel review discussion at that time. Thanks.